Hello everyone, my name is Srihith. My paper ID is BH5107. My paper title is CropViT, Climate Aware Vision Transformer Model for Crop Yield Prediction. Introduction. Crop yield prediction is critical for effective agricultural management and for mitigating supply chain risks, as farmers need accurate forecasts months in advance to make informed decisions. However, traditional methods such as relying on vegetation indices or ground-based data often face a significant timing gap. This information frequently isn't available until a crop is halfway through its life cycle, leading to reactive monitoring after the key window for intervention has already passed. To address these challenges, we introduced CropViT, a climate-aware vision transformer model. Our model is designed to identify yield prediction months before harvest across diverse crop types, maintaining high performance stability even under volatile climate conditions. Related work. First, we looked at traditional statistical regressions. While they are the industry standard for decades, they simply cannot handle the complex nonlinear biological responses crops have to extreme climate stress. We then saw a shift towards convoluted neural networks, or CNNs, which significantly improved how we extract spatial features. However, CNNs have a fundamental limitation is that they struggle to connect data points across long distances across diverse landscapes. Today, the state-of-the-art methods involve fusing satellite imagery with local weather data using masked autoencoders and graph transformers. Our work, CropViT, builds on this evolution, specifically focusing on how vision transformer architecture can better handle these long-range dependencies that previous models have missed. Dataset. We use the CropNet dataset. CropNet is an open-source large-scale dataset designed specifically for multimodal climate-aware crop yield prediction. It is a collection of satellite imagery and meteorological variables across 2,200 U.S. counties across 6 growing seasons from 2017 to 2022, covering a variety of environmental conditions, including extreme weather as well as high yield periods. We used the high-frequency Sentinel-2 satellite imagery focused on red, near-infrared, and short-wave infrared bands. The short-wave infrared band specifically provides direct indicators of leaf water content and canopy moisture stresses. These features are often invisible to standard RGB spectrum but are highly predictive of yield. To ensure early crop yield prediction, we only use observations from the first 60 to 90 days of the growing season. The ground truth yield data for corn, soybean, and winter wheat are sourced from the USDA National Agricultural Statistics Service at county level for bushels per acre. We spatially align the Sentinel-2 image patches with county level yield reports. Each county is represented as a series of 224 by 224 image patches, which is output sequence for our vision transformer encoder. Methodology. This is the architecture of CropViT for early seasonal yield prediction. CropViT uses satellite imagery and climate data. It begins with Sentinel-2 input images at 224 by 224 resolution, incorporating RGB, NIR, and SWIR bands. These additional spectral bands are particularly important for agriculture because they capture vegetation health, moisture levels, and crop stress signals beyond what standard RGB imagery can provide. The image is divided into smaller patches and each patch is converted into an embedding vector. Since transformers don't inherently understand spatial layout, position encoding is added to preserve the spatial structure of the field. These patch embeddings are then processed through multiple transformer encoder blocks, each consisting of multi-head self-attentive and feed-forward layers. The self-attentive mechanism enables the model to capture long-range dependencies across the entire field, allowing it to learn global relationship between different crop regions rather than only focusing on local patterns. In addition to image features, we include climate variables such as temperature and rainfall. These features are fused into the transformer pipeline, enabling the model to learn both from spatial crop conditions and environmental factors. A special classification token aggregates information from all patches to form a comprehensive field-level representation. This representation is passed through a regression head to predict crop yield in bushels per acre. Overall, CropViT combines remote sensing images and classification of climate intelligence to deliver scalable data-driven yield forecasting. For evaluation, we used the 80-20 train test split where 80% of the data was used for training and 20% reserved for testing. We applied stratified random sampling to ensure balanced yield distribution, preventing bias towards specific yield ranges. The model was trained on an NVIDIA A100 GPU, enabling efficient processing of the transformer architecture. Results: we evaluated CropViT against two established baselines, a LSTM and a ResNet 50. As you can see from the RMSE chart on the left, where lower values indicate better performance, CropViT consistently achieves the lowest error across all three crop types. The most dramatic improvement is seen in corn, where we reduced the RMSE from roughly 18 to just 11.5 bushels per acre. If we look at the R-square score on the right, CropViT reaches an impressive R-square of 0.81 for corn, 0.79 for soybeans, and 0.76 for wheat, significantly outperforming both the LSTM and the ResNet 50. These results demonstrate that by using the vision transformer architecture, we are much more effective at capturing the complex long-range spatial and temporal dependencies required for accurate early season yield prediction. CropViT is more accurate and works well across different farming conditions. We also conduct an ablation study on corn dataset. The full CropViT model achieves an RMSE of 11.5 and R-square of 0.81. Removing climate injection drops the R-squared to 0.77, proving that climate data is key predictor. However, the most important impact comes from the global attention. Without it, the RMSE climbs to 13.6 and R-squared falls to 0.72. Limitations. There are some practical trade-offs and limitations of this approach. While CropViT is more accurate and the self-attentive mechanism leads to a 1.8 times increase in inference time compared to standard CNNs, which is a factor to consider for large-scale deployments. Additionally, differences in detail between satellite maps and weather data can sometimes hide local crop conditions, and heavy clouds often block the satellite sensor's view. In conclusion, CropViT provides a highly accurate early season yield forecast that outperforms both traditional and CNN models across multiple crop types. The model demonstrates strong predictive performance and generability across diverse climate conditions months before harvest, achieving RMSE of 11.5 and R-square of 0.81 for corn. By effectively capturing long-range spatial dependencies, CropViT successfully links specific environmental stresses directly to final yield outcomes. Future work. We will extend the CropViT framework by adding more fine-grained temporal details to better capture dynamic growth stages of various crops and analyzing the impact of extreme weather conditions on the model performance. Since there is a 1.8 times increase in inference time compared to standard CNNs due to the model's self-attentive mechanism, future work would include improving efficiency and optimizing the model. Thank you.